Right, so we're now feeding AC into a circuit which is purely resistive. Purely resistive, there's no reactive component. A reactive component is something which varies its impedance according to frequency. Now what we could do here that's interesting, because inductors and capacitors are reactive, I'll say that again, they change their apparent impedance, which is AC resistance, according to the frequency they're operating at. So what I'm going to do here now is I'm going to go into R2, and I'm going to say R2, I don't want a resistor there, I want a capacitor. So I'm going to click on R2, right click, and I'm going to replace components. I'm going to go below where it says resistor, I'm going to go to capacitor, click on capacitor. 1 micro will do, it's not particularly critical what size it is, but 1 with the mu symbol means 1 millionth of a farad. I'm going to click OK, and you'll notice straight away that it's replaced that in my circuit. So what you might say? Well, I said to you before that the capacitor will change its impedance according to the frequency. The resistor doesn't. Or ideal resistor doesn't. So if I put 1 hertz in, the resistor would behave exactly the same in principle as a 1 megahertz or 1 gigahertz input signal. Not so with the capacitor. Let's see that for real. So what am I going to do? The first thing I'm going to do is I'm going to go to my AC signal here, and I'm going to say I'm going to put in a low frequency. Well, what's a low frequency? I don't know, 10 hertz, something like that. That's really low. Let's go 50 hertz because that's mains. Okay, so 50 hertz, click OK, and then I'm going to have a look at what the output waveform looks like. Well, I can't really see it because I've got to change the time in the bottom left-hand corner. And by changing the time, of course, then I can get it into the window and see it. And the analogy I used yesterday, it's a bit like going up to Wivenhoe House and photographing your friend in one of the squares. You're not going to see them because they're too far away, but if you get too close and poke the camera into their ear, you're not going to see them either because you can get a photograph of their ear. So you need to be a sensible distance away, and that's what you're doing with time here. You're adjusting the time until the waveform looks like you want it to look. Sometimes you want to see it in that kind of form, sometimes you want to see a bit more of the gradient inside the waveform. Okay, so we've got that, but note the amplitude. So peak to peak, it's about 5, or let's have a look at VP from the halfway line. It's about 5, 10, about 13, 14 volts, something like that, isn't it? From the halfway line, yeah? We're not interested in the absolute measurement, we're just interested in how tall the waveform looks. Okay, so that's 50 hertz. Let's stop the simulation. Now let's put 5,000 in here. Click OK, so we've now got 5 kilohertz going in there. Now let's run it. And look what happens. Look what happens. Don't change the scale on channel A. What you've got there now is all the amplitude is gone, isn't it? And you've got almost a straight line there. You would actually have to magnify it by changing the volts per division here. And if I do, you will actually see that is a sine wave. If you play about with the time base, there we are. That's a sine wave. But now we're on 200 milli. That's 200 1,000ths of a volt. So the conclusion is there that if I go back to 5 volts, look how small that waveform is. Well, let's take a halfway house. Let's go into 2 kilohertz, something like that. We go to 2 kilohertz. What I would expect is a slightly bigger waveform now, yeah? And there we are. So experiments don't tell lies, do they? Or they shouldn't. sine wave there. Let's make the sine wave a bit bigger by decreasing the frequency a bit more. So let's go to 1 kilohertz. Okay. And lo and behold, the waveform's bigger. Let's stop that. And let's go to 500 hertz. Click OK. And it's bigger still. Yeah? Successful approximation, so let's go to 250. Click OK. Run it. And we're bigger still. So you see what's happening here. The output is dependent on what frequency I put in. The amplitude changes according to the frequency, not according to the amplitude. I have a frequency selective circuit. So do those experiments that I just did, put some more values in and verify for yourself what happens as you increase frequency, what happens as you decrease frequency. Now just in summary, what happens as you increase frequency, C1 goes into conduction and connects the output to ground. Yeah? When you're at low frequency, the capacitor doesn't go into conduction, so you see the waveform that you're putting in. It's as simple as that. But the mathematics behind it is slightly more difficult to grasp. Okay? So a frequency selective device. It's a filter, is what that is, because I could change those components such that I could remove high frequency noise, for example on a telephone line. So I could get rid of the shh noise, which is at the high end, which will be annoying to me on the telephone, with a circuit as simple as that.